All right, guys, day 2 of solving differential equations. More of the same stuff. We're still going to be doing the separate and solve method of solving differential equations. We're just going to see some different functions than we saw yesterday and how to deal with that. All right, so first example, we're going to have to get our y's on the left side. So we're going to be dividing by y here, and we're going to multiply by the dx over here. So we're going to end up with, I'm going to write it like this, 1 over y dy. We could also put that dy on top like I did in yesterday's lesson, but I think it'll be a little clearer what's going to happen here if I write it like this. All right, then over here we're going to have our 6x squared and our dx. All right, once we get our variables separated out, that's when we integrate both sides. Okay, so remember 1 over y, you cannot use the power rule there because we'll end up dividing by 0 if we use the power rule. So got to avoid that. The integral of 1 over y is the natural log of the absolute value of y. Absolute value is actually quite important here. So you want to make sure to include that because that's going to have some more effects later on in the problem. All right, then on this side, that's going to be 6x cubed over 3, which will reduce to 2x cubed. And then don't forget our constant of integration. All right, if you remember from day 1's lesson, I like to go ahead and plug in the initial condition right now. So we can go ahead and figure out our c, and then we'll worry about solving for y at the end. All right, so if we plug in -5, we end up with natural log of 5 because the absolute value turns that -5 into a positive 5. All right, over here we just get 0, so that's going to end up being c. So natural log of 5 is c, so our equation will be the natural log of the absolute value of y is equal to 2x cubed plus the natural log of 5. All right, so now our goal is to get y by itself, so we need to get rid of our natural log. We do that by making it an exponent of an e base. So we're going to do that same thing over here, and make sure we're taking this entire thing as the exponent of e. All right, so over here, those are just going to cancel out, and we're left with the absolute value of y. It is important that you still include the absolute value bars here. We'll get rid of them in a second. All right, over here, we're going to want to use an exponent rule. Whenever you add the exponents together, that's the same thing as multiplying like bases. So I can take an e to the 2x cubed, just that part by itself, and then multiply that by another e to the natural log of 5. All right, now let's focus on this e to the natural log of 5. That's a constant. And the e and the natural log actually cancel each other out, leaving you with just 5. So I'm going to take that 5 and I'm going to move it to the front. So it's going to be 5 e to the 2x cubed is equal to the absolute value of y. All right, so we're really close here. All we have to do is get rid of our absolute value. Okay, so we can just drop the absolute value bars. However, when you do that, that means that the other side of the equation could be a plus or minus. So this is the same as like taking a square root of both sides. We have to say which one it is. Is it a positive or is it a negative? All right, and just like with square roots in our lesson yesterday, it always goes back to that initial condition. All right, the only way that this exponential can be a negative number, exponentials are always positive unless they have a negative in front of them. So the only way we can get a negative y value is if the function has a negative in front of it. So -5e to the 2x cubed. That would be it. All right, if you're feeling up to it, give this next one a try on your own. Remember, you can rewrite that y prime as dy over dx. That'll be the first thing I do. This one's a little tough, but I would encourage you to give it a try. Pause the video, and then unpause and come back and see how you did. All right, so I'm going to rewrite this as dy over dx. I'm also going to separate this out just so you can see what's happening here. So I'm going to put the y plus 3 out to the side and then multiply by 1 over x squared. So we want to leave the 1 over x squared where it is because we're going to be multiplying this dx over here as well. That means we're going to need to divide by the y plus 3. So we're going to end up with 1 over y plus 3 dy is equal to 1 over x squared dx. All right, we have our variables separated out now, so it's time to integrate. Okay, remember when you have 1 over a y to the first power, even if it's added with a constant here, that's going to be a natural log, same as our last problem. So we're going to get the natural log of the absolute value of y plus 3. All right, over here we have an exponent on our denominator, so we are not going to get a natural log here. We're going to use the power rule. This is x to the negative 2, so we add 1 to that and we get x to the negative 1, and then we divide by negative 1, or we just put a negative in front. And then we don't forget our plus c as well. All right, let's go ahead and plug in our initial condition right here. So we end up with the natural log of 4, plugging in 1 for y, and then here we end up with negative 1/2, moving that x to the denominator and plugging 2 in for x. So we'll need to add that 1/2 over. These are not going to be like terms, so we're just going to leave it like that. All right, so let's go plug those back in. So we have the natural log absolute value of y plus 3 is equal to negative 1 over x plus natural log of 4 plus 1/2. All right, so we are now going to get rid of our natural log. So we're going to make this a power of e. And so over here, this whole thing, all 3 terms, become a power of e. All right, so we're left with an absolute value of y plus 3. All right, and so this is going to basically become 3 different e's. We're going to have e to the negative 1 over x, e to the natural log of 4, and e to the 1/2. The e to the natural log of 4 becomes just a 4 in front because the e and the natural log cancel out. These other 2 don't cancel out, so we're going to combine them together by using the exponent rule where we can add the exponents. And I'm actually going to switch them around. So I have e to the 1/2 minus 1 over x. All right, and then we still have our absolute value bars here. Okay, so finally we can get rid of our absolute value bars, y plus 3. And we have to make sure to put a plus or a minus sign. This time we want a plus sign because our initial condition is a positive number. So we're good to go there. Nope, we don't have to write a plus sign obviously, but we know it's positive. And then I think I'm going to get a common denominator here. So if I multiply this by x over x and 2 over 2, I end up with x minus 2 over 2x as my exponent there. All right, last step would be to subtract that 3 over, and we have our answer. All right, last one we're going to look at for day 2 is going to be a word problem. So this will be what it's going to look like most likely on the free response section of the test, which it seems like that's going to be the entire test now that they've come out and said you're taking a shorter exam, going to be all free response questions. So I would expect to see one very similar to this on that test. We'll find out if what's going to be on that test on April 3rd. So we'll talk more about that then. All right, so the rate at which a puppy gains weight is proportional to the difference between its adult weight and its current weight. All right, so we talked about these problems on day 1. All we did was set them up. Now we're going to actually solve one as well. So at time t equals 0, when the puppy is first weighed, it is weighed at 3 pounds. So that's an initial condition. They also gave it to you in the form you're familiar with down here. If p of t is the weight of the puppy in pounds at time t days after it is first weighed, then dp over dt equals 1/5 times 75 minus p. So that whole thing at the beginning, they have told you what the equation is right here. So you don't actually have to write your own equation. Makes this problem quite a bit easier. All right, so let y equal p of t be the solution to the differential equation with that initial condition. Use separation of variables to find y equals p of t, the particular solution with the initial condition. All right, so basically they give you an equation, they want you to solve it. So we're going to use our separation of variables to do that. So I'm just going to rewrite the equation down here. All right, so I want to get my p's on the left side. So I'm going to divide by 75 minus p. So I'm going to get 1 over 75 minus p times dp. And then I'm going to leave the 1/5 here and multiply by the dt. All right, time to integrate. So we have a fraction where we have a p to the first power. So that's when you get a natural log. So natural log, absolute value of 75 minus p. Okay, you have to consider a u substitution here. Now, I like to do this one in my head because I don't want to waste time writing it all out. But if you're not seeing it in your head immediately, you may want to write it out. U equals 75 minus p. So du equals negative 1 d p. So you get this extra negative 1 constant. So your new integral would have to have an extra negative in front of it. So our natural log has to have a negative in front of it. All right, you don't need to write this down if you don't need to on that one. Anytime you have a negative variable, you're going to get a negative constant in front. All right, over here, we're just integrating a constant. So all you do is put on the variable 1/5 times t, and then don't forget about your constant of integration there as well. All right, like we've done on our previous problems, I want to go ahead and plug in our initial condition right now. So I'm going to plug in 3 for p. So I end up with negative natural log of 72. And I don't really need the absolute value bar there. Get my 7 back. All right. And then plugging in 0, so that's just going to cancel that t term out. So c is equal to negative natural log of 72. All right, so now we have negative natural log of 75 minus p with our absolute value bars is equal to 1/5 t minus natural log of 72. All right, so we need to get rid of this negative first before we can do our exponential function to get rid of the natural log. So we're just going to multiply everything by negative 1. So natural log of 75 minus p is equal to, and I'm just going to switch these around. So natural log of 72 minus, let's make this t over 5 just to simplify what we have to write. All right, now we can do the exponential function on both sides. Again, make sure that both terms here are getting becoming the exponent of our e. So we end up with the absolute value of 75 minus p. And then over here, we're going to separate this out. E to the natural log of 75 times e to the negative t over 5. All right, so this e and natural log cancel out, leaving us with 75. And we're left with e to the negative t over 5 there. And then we can drop our absolute value bars, but we have to decide whether this is a plus or a minus. So back to our initial condition that we plugged in, it was a positive 3. So if I'm going to get a positive number, I need a positive variable. It's always going to be the same sign as the initial condition. So if the initial condition is negative, you're going to put a negative there. If it's positive, you're going to leave it positive. All right, so last step is to get p by itself. So I like to think of this as I'm adding p over to this side. And I just realized I did something wrong up here, so I'm going to go back and fix it real quick. This is natural log of 72, not 75. So all these 75s right here are actually 72s. All right, so back to finishing this up. I like to think of this as adding p to this side and subtracting the 72 over here. So we end up with p equals 75 minus 72e to the negative t over 5. And that is it. All right, so hopefully you practice some of these problems on the worksheet number 2, and I will see you next time.